Okay, this is another problem I take from the past year's final. The model is like this. This is not the, if we compare with the predator-prey problem, this is actually not a predator-prey, right? Predator-prey, we have one positive, one negative. We have one positive and negative for the second part. Okay, if we see the outline that we have before, there are three problems. This is not a predator prey. The second problem for competing species, we have positive for both. Okay, we have growth with a natural rate. Okay, but this is different. It has negative here for each of the population, means there is decline when when another species absence. Okay, and we have positive when due to the interaction between the two species, it leads to the increase of each population. Okay, example is bee and a nectar of a plant. Okay, this is the case where it has a mutual cooperation between the two species. Okay, mutual cooperation. So in this problem, a bee and nectar of one plant species simultaneously pollinates the plant. Okay, so if the survival of the two species depends on their mutual cooperation. Okay, so what does the terms means here? If there not exist the plant, so a bee will decline. Okay, the bee population will decline. And if there exists the plant, then the interaction between the bee and the plant would leads to the growth of the bee population. Okay, that's why we have negative sign here. In the absence of the plant, we have positive if there exists the plant and they interact with each other. Okay, mutual cooperation. The same with the bee here, represent the bee. Okay, population B. P here represent the population for the plant. Okay, the same here. If we have negative sign here, because in the absence of the bee population, the population for the plant will decline. And here positive if there is existence of the bee population, the plant would grow as well. Okay, so I proceed with the question here. Okay, find the equilibrium point of the above system. Okay, actually the step by step is just the same as what we see in the predator prey problem. Okay, in terms of finding the equilibrium points, in terms of the type and the stability. Okay, but the type may be a different type. The long-term solution may be a bit different. Okay, so in this case, question 1, the equilibrium point. So as usual, for the equilibrium point, we take the right hand side, we can make it equal to 0. So for the first equation, I will factorize b. So we'll have like this, 2 plus 5b equals 0. So from here, we able to have two equations. The first one is b equals 0. Another one is minus 2 plus 5b equal to 0. And from the second equation, I can factorize p. So we have p minus 3 plus 3b equal to 0. So here we'll get two equations as well. P equal to 0 minus 3 plus 3b equal to 0. Okay, so as usual, we pair. If we have p from a b from here, then we have to take p from the second equation. So means here, this I can combine with this p. So I will get, the first equilibrium point for this problem is 0, 0, b equal to 0, p equal to 0. And if I take b from here, it doesn't mean, it means nothing, right? Because here b0 we cannot get p, okay? But the second equilibrium point can be obtained by solving these two equations, okay? So from these two equations I will solve, okay? B equal to 1, okay? So from here we get P equal to 2 over 5. Okay, so this will becomes the second equilibrium point for this case. We get the second equilibrium point comes from this is 1, 2 over 5. Okay, which equilibrium point is a stable one? So to check the stability, we can refer to the stability table. But before we refer to that table, we need the info about its eigenvalue, right? Okay, so to answer the second question, we have to find the eigenvalue for each of the point, okay, for point 0, 0, and also for the point 1 and 2 over 5. So in this case, the first equation A, matrix A is, okay, from the first equation we have to differentiate. Okay, before that, before this I mentioned that it's either you differentiate Jacobian or you factorize. So actually if you factorize, you in some cases it will be different compared to using the Jacobian. So be careful, make sure, I think better use the factorization or Jacobian matrix. Okay, so factorize the first term, factorize with respect to b, okay, because before this we see x and y. So now the equation that we have is p and b, so you have to change accordingly to find the Jacobian matrix. So matrix A here is differentiate with respect to b from the first equation. We have minus 2 plus 5b, and then differentiate with respect to p, here becomes positive 5b. And then from the second equation, in its Jacobian matrix, here differentiate from the second equation with respect to b becomes 3p. And here the second equation differentiate with respect to p becomes minus 3 plus 3b. Okay, so for each of the equilibrium point that we have, we can find its eigenvalue. Okay, so for equilibrium point 1, we can have its Jacobian matrix at point b0, p0. So we substitute the value for p0, the value for b is 0 as well. We will get minus 2, 0, 0, minus 3. Okay, so next we can find its a minus lambda I equal to 0, determinant. Okay, so means from this matrix, we will have the determinant of minus 2 minus lambda here, 0 here, 0 here, minus 3 minus lambda equals 0. And solving this, we get minus 2 minus lambda minus 3 minus lambda equal to 0. So we have two eigenvalues here. Both are real value. Lambda equal to this is minus 2, and the second one is lambda equal to negative 3. Okay, so this actually referring to the table of stability. This is actually a stable one. So next, we can check for the second equilibrium point as well. So for the second equilibrium point, we do the same process like this to obtain the eigenvalue and to check its stability. So we will have for equilibrium point 2, the point is equal to 1 2 over 5. Okay, 1 for B, 2 over 5 for P. So we substitute the values for P equal to 2.5, for B equal to 1. We calculate into this, we get the matrix for it is minus 2 plus 2, so 0. Here 3P, so 6 over 5. Then 5B is 5. Here minus 3 plus 3, so 0. This is matrix A for the second equilibrium point, 1 to 5. So we have A at this point, minus lambda I. We have to calculate in order to get its eigenvalue. So 0 minus lambda, here 6 over 5, 5, 0 minus lambda, determinant equals 0. So we have lambda square minus 6 equals 0, where we have lambda equal to plus minus square root of 6. Okay, so this is the real value. Okay, one of it is positive, one of it negative. Refer to the table of stability. We have the type for this. I don't remember. Please refer. Okay, the stability is unstable, not stable. I don't remember exactly. Okay, that is I think unstable. Okay. So the answer for this part. Okay, so which equilibrium point is a stable one? We already identified. Okay, it is the first equilibrium point, 0 0. The third question, based on the given phase portrait, discuss the long-term behavior. Okay, so I will discuss later for this. I need to get the phase portrait first.